But I'm here today to talk about our co-design project, which is the co-design of FeNN, which is a RISC-V vector processor for spiky neural network acceleration. And we're both from the University of Sussex. So when we're thinking about accelerating something, we need to know what type of computation we're accelerating. And my PhD student Balazs did a great job of explaining this earlier. But spiky neural network computation is a hybrid system. So it's got two components. You've got some free dynamics, in this case, a leak integrating fire neuron. You've got two state variables with some kind of dynamics. These can be much more complex than this with a more complex neuron model, but you've still got these kind of continuous dynamics. And then there's some transition condition, which emits events. There might be more than one transition condition. As someone was talking about earlier, you can have multiple output neurons. You could have multiple transition conditions. And at various types of transition, some reset happens. So some non-differentiable event happens. So in this case, with lift neuron, you reset the voltage to 0. And the other type of transition is when you get a weight, when you have an incoming spike. And in this case, a weight gets added to the I variable. So spiky neurons are a hybrid system. How do we implement this? There's lots of ways we can implement this, as Jimmy alluded to earlier. But I'm going to talk here about the kind of hybrid approach, which is what's used on Loihi, Spinnaker, lots of software simulators. So in this approach, you have a time-driven component, which updates one time step of neurons, and an event-driven component, which handles all the events that happen in that time step. So in this time-driven approach, the first to notice is that there's lots of memory accessing. You have to load all your state variables at the start and write them all back at the end. And in the middle, there's some small amount of maths going on, and this has got an arithmetic intensity, thanks to Emre for introducing this earlier, of about one operation per word, which, like the softmax, is pretty low. And then we look at our event-driven part. Like you load your current input, then you loop through your spikes, you add some weights to it, and you save it back. So this is even worse. This has got an arithmetic intensity of like less than 1, depending on how you slice it. So all in all, spiky neural networks, they're a very low arithmetic intensity problem. So the kind of hardware developments that we're seeing in mainstream FeNN accelerators are kind of not quite right, because FeNNs are very arithmetic intensive. The main computation is matrix multiplication, where you basically load tiles of matrix into memory, and you perform large numbers of math operations. So GPU architectures have kind of evolved to reflect this. So you see here, modern GPUs are somewhere around this 100 operations per word read from memory, and our SNNs are only 1. So we're kind of floating here in this green line. Our ideal system would have been some 90s NEC supercomputer, which isn't really ideal. And this means that spiky neural networks are very memory bound on GPUs. And this is the answer to, I can't remember whose question from Balazs's talk, that on the Jetson, on Tom's talk, on the Jetson, all these kernels are memory bound. Like there's no real computational problem, it's just memory bound. So how can the situation be improved? Well, you can use sparsity. So you want to have temporal sparsity, so events rather than continuous updates. And you want to have spatial sparsity, so sparse weights rather than dense weights. And you want to have low precision types. If you make the type smaller, you need less memory bandwidth. You're reducing the memory bandwidth. And most digital neuromorphic systems do all of these, probably. And the other alternatives, you can increase external memory bandwidth, which is maybe we probably can't increase it much more than GPUs, or we can add more local memory. And again, this is what most digital neuromorphic systems do. It's not novel thought. So what hardware can we use that might be a better fit for this? So we've got GPUs. They've got a very high external memory bandwidth. They've got very small local memory because they're dedicating all their area to Mach units and CUDA cores. If you've got make an ASIC, you can do whatever you want, but what you do is proportional to how much money you have. We don't have very much money. So field programmable gate arrays, which are kind of programmable chips where you've got some kind of ASIC components, so SRAMs, multipliers, this type of thing, are quite an interesting proposition here. So they've got high memory bandwidth because the high-end ones come with high bandwidth memory. They've got lots of local memory, probably 2 or 3 times an equivalent GPU. We've only got moderate compute power, but probably enough for SNNs. And personally, haven't been slightly ruined by working with GPUs. They come in a whole bunch of sort of useful form factors, and they're kind of in-memory accelerators. So we've got a Kriya. This is sort of Jetson drop-in. It costs a few $100. It's got about 4 gig of DDR4 memory externally. It's got a few meg of onboard SRAM, and it's got quite a lot of FPGA fabric. And then if we go up the spectrum, you get this thing called like an Alveo system, which is sort of a V100 alternative. This has got 60 gig of high bandwidth memory and 40 odd meg of on-chip memory. So it's more than you get on an equivalent GPU, and it's not cache, it's programmable, it's user-controlled scratchpad memory. So both of these things are kind of in-memory accelerators as well, which I think is something that's underlooked at in the neuromorphic community. Having an in-memory accelerator is really nice as you integrate with applications much more easily. Yeah, so they're kind of inherently kind of potentially easier to use, easier to integrate. So what are we going to build? There's lots of fixed function FPGA spiking neural network accelerators, including one by these guys here, which looks really cool. And this is potentially an awesome match for deploying spiking neural networks. A lot of the advantages apply equally here. But we want to build something flexible, a flexible accelerator of researchers. So sort of at the top end of the cool triangle diagram we really had the last talk, kind of tens of watts to hundreds of watts accelerators for kind of bigger problems and research and training. But the problem with this, if you have to resynthesize your design to change your neuron model, no one wants to do that. I can only use Xilinx tools with Zainab's help. And I don't think most researchers would really think that's a great idea. And as spiking neural networks aren't compute bound, it really doesn't matter what it does. You don't really need to have optimized compute. Swing program was probably fine. And this is not a novel idea. In fact, I started my neuromorphic career looking at systems like this at Cambridge, and people have made similar things since. So now I'm going to hand over to Zainab to talk about what we built. Yes. I'll come back at the end to waffle some more.
Yeah. Okay, I'm Zainab Aizaz from University of Sussex, and I'm going to explain you our design, FeNN. FeNN is FPGA Enhanced Neural Network. It's a RISC-V processor for SNN acceleration. It's fully programmable. So FeNN has 2 main parts. First is the scalar core. It's an open source RISC-V processor from ETH Zurich and Open Hardware Group, which is CV3240X, which is scalable, customizable, and to fit it on FPGA. Originally, it's designed for ASIC, but we fit it on FPGA, and so we change its memory, its load and store structure, and its prefetch logic as well. The part of FeNN, which is completely developed by us, is a vector coprocessor, which is a coprocessor to RISC-V, and we have developed it completely. It's developed in system Verilog. So why a vector processor? Vector processors are implementation of SIMD, single instruction, multiple data. So if you are in software, you are using Python, and you want to multiply 16 numbers, what you do? You create 2 arrays and multiply. Simple. But in hardware, what you do? You have a multiplier, and you go one by one, and each multiplication, you have to do 16 times, right? So the speed is too slow. So to accelerate it, what we can do? We can create a vector having 16 operands and 16 hardware multipliers so that all the multiplication can take place parallelly. This would increase the hardware, of course, but the speed is worth it. So why here we want a vector processor? Because this is the era of ASICs, and which are too expensive. So FPGAs are always lagging behind ASICs in terms of clock speed, right? So if we make a vector processor, what we can do? We can perform 32 operations. Suppose the number of operands in each vector is 32. So we can perform 32 operations in 1 cycle, which is massive. So we can beat ASIC performance. I want to explain you some of the features of vector processor that we have in FeNN. It is a 3-stage pipeline. Originally, RISC-V is 4-stage pipeline, but fetching we are doing in RISC-V. So our vector processor is a 3-stage pipeline. I hope I can explain pipeline operation to some of you, or if not everybody know it, I want to explain what is pipeline architecture. So in a non-pipeline processor, you have 2 instructions. Let's see the blue instruction, which is the first one, and the red instruction is the second one. Each instruction takes 4 cycles to complete through 4 stages, which is fetch, decode, execute, and write. So when first instruction finishes, then in the next clock cycle, second instruction starts. What's the drawback in non-pipeline architecture? When first instruction is in execute stage, the decode and fetch stages are idle, and efficiency is wasted. Speed is also less. But in a pipeline architecture, what is the principle? When first instruction is in decode stage, second instruction is fetched. When first instruction is in execute stage, second instruction is decoded, and third instruction is fetched. So your hardware units are never left idle. But this requires complex programming, right? So we have made it pipeline, a 3-stage pipeline. That means this first cycle takes place in RISC-V processor, but all the remaining cycles goes to vector processor, and then the whole instruction finishes in 4 complete cycles. Now, another property or another feature of VEC is lanes. Lanes means how many operations you are using, how many operands you are using in your vector. Suppose you want, as I explained, that 16 multiplication. So your vector is composed of 16 operands. FeNN uses 32 operands. So the vector is composed of 32 operands, and each operand is 16-bit. That's the lane width. So what is the register file width? 32 into 16. That is 512-bit of register file that we have. Any processor has a raw hazard, read after write. If your second instruction requires the output of previous instruction, but it wants it at this stage, but this first instruction is not yet completed. So what does it do? It gives a wrong output, which is called a hazard. To remove hazard, we have made such a logic so that whenever the result is obtained, we just fetch from that place, and we do not wait for the instruction to complete and fetching it from the final destination. Did you get my point? That the result is obtained in execute and write stage only. Until decode, we don't have any result. So whenever the first instruction in these 2 stages, if the second instruction needs the result, we take it out from those places where it is right now. So this is called the forwarding logic, and it's efficient for more speed because you have just executed one instruction, you have performed one thing, and in the second instruction, you want the result of that. So forwarding logic also we developed in FeNN vector processor, and for raw hazards, we have done that. Then we have an instruction set of 16 instructions. What is an instruction? All our computers don't understand our language. They understand assembly language. So to convert it, we need an instruction, and it is a set of commands that gives instruction to a computer to perform some task, right? So in our vector processor, we have 16 tailored instructions tailored to SNN. So they perform SNN fetching, SNN any processes efficiently. These are vmul, vstore, vcell. I'm explaining you vmul, right? So what is here? Vmul, v6, v2, v4. We multiply vector operands in register 2 and register 4 and save it in register 6. This is what that instruction says. So how do we encode it in an instruction? Opcode. It symbolizes what kind of instruction it is. For 10, we have used arithmetic instructions, right? 100, we use for vstore and others. This is opcode. It is a 7-bit field, right? Then RD is the destination register. You can see it's 6. As vmul says, you have to store in 6. Then funct represent 3 digits of arithmetic. If it's 100, it's vmul. If it's 000, it's vadd. If it's 001, it's vsub. So then we have RS1 and RS2. You can see it's 2 and 4. That means take operands from 2 and 4 and save it in RD, the destination register. That's what vmul says. And in final, we have some specific instructions like shift, if you want to shift after multiplication, if you want to round it. We have stochastic rounding, which symbolizes 1, 0. We have no rounding, which says 0, 0. And finally, the saturation bit, if you have overflow in your output, that gives wrong results. So if we have 16-bit operands, so we saturated 2 plus 32767 and minus 32768. This is what a vmul instruction would look like in our processor. So how does execution of a LIF, leak integrate fire neuron, takes place in our processor? Firstly, with some more instructions in the beginning, using RISC-V and other vector load and store instruction, we have saved spikes, voltages, and weights in memories, right? And those memories, we have saved it to the register file. In which register? Here, vmul is different. V9, V3, and V7. 7 is the shift. We want it for SNN. So V3 and V9 have operands. stored in the register file, right? So how does VMAL execute? Instruction is offloaded to the instruction memory by a processor. I would explain in the next slide how it is offloaded. But now instruction goes, then instruction is decoded, whether it's VMAL, VAdd, which registers it wants, okay? Then execute unit is where arithmetic and logic unit is there. It performs multiplication, right? Because it's a VMAL. And I'll explain you what is randomness, but let us go for this first. And then it multiplies and writes back. This is how a VMAL is executed in FeNN, and this is how other instructions which are written over there will be taking place. I hope you got it. So other circuits, other important circuits of our FeNN are random number generator that's useful for executing adaptive leaky integrate fire neuron. Okay, so if we would have built this using common register file of RISC-V, we would be needing an extra port, which would make the hardware too much, increase the hardware. So what we did, we made a special Zoroshiro random number generator, which is hardware friendly, means it's made using XOR gates and NOR gates, very small. And then we have made 2 special registers for RNG operation only. Also, we did stochastic rounding. I'll explain to you later why it is good for simulating ALIF neurons. It's efficient for them. So how do we do stochastic rounding? You can see A into B multiplied, 2 operands are multiplied, with some randomness is added. And then operation is shifted. Now A into B plus R, that's the output of stochastic rounding. And N is the shift. Why do we use that shift? A into B, 16 into 16, 2 operands are multiplied, the output is 32. Randomness, we added to it, now we get an output. Why do we shift it by N is equal to 16? Because we want the output to fit into register file again. We did not increase the size of the register file. Instead, we made it a little more inaccurate by shifting it because we want a compact circuit. Next, this is the entire design. We made our FeNN a single core on KV260 Kriya board, which is from Xilinx. And Xilinx is already equipped with ARM processor, which ARM processor holds the complete C++ assembler code that it copies to instruction memory using AXI interface, Advanced Extensible Bus Interface, which is what is used by ARM processor to control the block memories in this design. And then those block memories are shared by FeNN, while URAMs, UltraRAMs, are not using any AXI. They are directly connected in a standalone mode. So this is a simulation of Poisson over FeNN. So histogram shows in the left diagram that histogram has 3,200 Poisson variates sampled from distribution with lambda is equal to 5. Also, in this diagram, the right side, we see that round to 0 does not give us good. It's really bad. But round to middle, this one, round to nearest is better, but still the rounding error is large for all the inputs. Here, in stochastic rounding for ALIF, what we can see, the rounding error is large, but not for many inputs. So stochastic rounding worked really well for us in simulating ALIF neurons. You can also see in graph A that we simulated 2 periods of Poisson spiking input using 64-bit floating point. Then you can see at the bottom, any design, any SNN in software, how do we execute 64-bit floating point, right? We don't have that much space on our vector processor. We are using 16-bit floating point, fixed points, right? So the dashed ones, the dashed lines in B top diagram are 64-bit, and the solid lines are simulated by FeNN with 16-bit fixed point. You can see there's a large deviation, so it's not that accurate. So what we did with stochastic rounding, in the bottom diagram, we have achieved something really close. That's how ALIF with stochastic rounding worked really well for our FeNN. Also, in the next one, what we did, same Poisson spiking input, but with increasing rates. This shaded area is again shown here. We have used 2 things, stochastic rounding with saturation and stochastic rounding without saturation. So the first graph is without saturation. So you can see there's a lot of deviation again here. So with saturation, the stochastic rounding worked perfect for us, which is shown in the last diagram, the bottom figure of D. We did inference of spiking Heidelberg digit data set, which is an audio data set recognizing 0 to 9 in English and German language. And we got raster plot of input and hidden neuron activity on FeNN. This one, this is a good result so far. I don't know what to say, but yeah, we're happy about it that FeNN was better than Loihi-1. Loihi-1. Okay, in time, in SNN simulation time. And then in C, we can see that different type of spikes had different types of instruction involved. This is just a common data that we want to share, that if we are having input spikes, we have more of memory instructions, like fetching from memory, a lot of that. And then hidden spikes, we have less memory instructions, more of arithmetic instructions. And then output, we don't have any memory instructions. We don't also have this green one. This is ALU instructions. So this is how our instructions are classified. These are our results. And for a fair comparison, we did not compare our design with any ASIC. We compared with FPGA accelerators that are already available and have done well. And those two are Snava and Gabon. We can see that Snava operated on 100 lanes and had frequency of 125 megahertz, had this much utilization. Gabon was very good in frequency, 286 on FPGA. It's really worth mentioning. And Gabon had, but it only used 8 lanes. So SNN model would be, a smaller model is implemented. And then ours is 166 megahertz, the mediocre of 2, but our utilization is better than them. In brackets, you can see utilization per lane. So whole of the resources divided by number of lanes, so we are excelling in that. And as far as energy is concerned, we have total inference energy that we calculated. We compared it with GPU and CPUs. So we got one half of GPU and 1/3 of CPU. The simulation energy is obtained by subtracting the idle power and the power for copying the data from memories to the input. So we remove from total inference energy the ideal power and the power of copying data, so we got simulation energy. And this is our simulation energy compared to JSON GPU, and divided by synaptic events, we got these results. I think Jamie would conclude after that.
Yes, thank you, Zainab. So as a PI, about 1 year into a 3-year project, I have about 85 slides of further work, but thankfully we're going to be cut short by time. So currently we're just using on-chip memory. But one of the cool things with these FPGAs is they have a very fast external memory controller, and we're developing a DMA engine to work with this. And this, we haven't fully hooked it up to FeNN yet, but this is our prototype, and you can see from the logic analyzer figure here that we're getting 512 bits of data from DRAM every 4 clock cycles, which is about what you need to provide synaptic weights to the event-driven part of the code, which is what it will be used for. So this looks really promising. And I think another really cool thing for the ecosystem, and kind of this was more by luck than judgment, Prophecy has recently released an event-based camera for Korea. So we're looking to build an IP to interface this camera directly with FeNN. And I think this is another really cool thing with FPGA, is that you can interface with whatever sensors you can imagine, with whatever hardware that you can implement. And this is a real problem with GPUs, right? You have to pause your GPU and synchronize the CPU every time step you want to do sensor data. So this is an area where we think this FPGA platform is going to be really exciting. And the ultimate plan for this project is we're going to make a 32-core version of this processor on this Alveo U55 accelerator. And as Balázs kindly explained earlier, event prop training has got the same kind of computational properties like the first table in this paper as inference. So we're going to do batch parallel event prop training on this 32-core version. And hopefully this will be a GPU beating spiking neural network accelerator, which is what we're dreaming to achieve. Oh yes, and the final piece of future work. I've been writing a compiler for this. Previously, I've been writing all the examples in assembly language, which has scratched the kind of masochistic programming assembly language itch, but probably not been very useful for other people. So we've been working on a compiler, which you can program this thing from Gen. And this is the first result, and it means nothing to no one apart from me, but I can tell you it's about 2 cycles worse than my hand-assembled version, which I'm perfectly happy with. And we ended before the end. Thank you very much.